Yeah, thank you, Sergey, for giving me the opportunity to present our work here for at least for me, new audience, I assume. I hope I can convince you that we have a future in liquid crystals, and by using new properties that are developing in time. So that's also the talk of my lecture, liquid crystal networks, and special class of materials for soft robotics, with ambitions for soft robotics, I should say. Just a brief introduction, who are not so familiar with liquid crystals and liquid crystal polymers. This way. I now do something wrong. I wanted to make this smaller. Yeah, hopefully I'm back again. Who are not so familiar with liquid crystals yet? Well, liquid crystals is a material which has a phase somewhere between the crystalline state and isotropic state, and was discovered at the end of the 19th century, and became interesting, especially also because of their electro-optical properties, which is used for many display applications. It took a while before people also start realizing that the polymer liquid crystal could also form polymers, and you could also get a liquid crystal phase in the polymer state. Some points to mention maybe in history. I mean, as the essays of Pierre-Gilles de Gennes, who at the end also got the Nobel Prize for it, and who predicted the many interesting properties if you bring the liquid crystals together into a polymer arrangements. The people in Germany, of course, Mainz and Freiburg later on, they were very active in creating different types of liquid crystal polymers, mainly side chain polymers or slightly cross-linked elastomers at that time. And of course, we should also mention the work at DuPont at the time, where Stephanie Kwolek developed their Kevlar fibers based on a material, aromatic polyamide, that has interesting properties and has kind of pleiotropic phase during the processing state, and is very strong because of its hydrogen bonding. I came into the field in the second half of the 80s last century, and I developed then while working at Philips the process of in situ photopolymerization of liquid crystal networks. And the difference with the state of the art at that moment was that I started with aligned liquid crystal monomers. So we modified the liquid crystal such that it could be polymerized by reactive end groups. It could be aligned just like the normal low molecular weight liquid crystals, and then by UV light you could photopolymerize the material to form a densely cross-linked network. So this is the first monomer that we synthesized for that purpose, and indeed you could convert it from the liquid crystalline state to the densely cross-linked liquid crystal network within a relatively high strength and optical anisotropy. Well, I was working at that time for Philips Research, and there was a reason why we developed that material, and that was the application in optical telecommunication fibers. The quartz fibers that are being used for that are intrinsically very strong, but when you draw them from a preform, as is shown on the left slide, so you start with the preform, and then you melt the material, and the preform already has a refractive index gradient needed for the total internal reflection of the light, and then when molten, you take it up in a spool. Now, quartz is intrinsically very strong material, but it has one problem. If it comes in contact with any other surface, easily surface stretches are formed, surface floors are formed, which reduces the strength enormously. And so it has to be coated online with the fiber drawing process, with polymer coating materials. And for that reason, people were using UV polymerization because the material must be has a low viscosity, because the speeding, the drawing rate is very, very high. It can be up to 10 meters per second, and the coating should be cured very fast. Traditionally, two coatings were used, the soft coating and hard coating. Both were polyurethane based. Well, at that time, there was a problem to solve, and that is the large difference in thermal expansion between the silica, which is 10 to the 4 orders or 5 orders of magnitude smaller than that of the polymer coatings. And that means if you coat the material at high temperatures, let's say 100 degrees or so, you have to cure it, also then it is heated, and then you start cooling it down to room temperature. The fiber, the coating shrinks faster than the fiber, and compressive forces are being built up, which leads to buckling of the fiber, mechanical instabilities of the fiber in the coating, and the buckling leads to optical losses. So the target now was to find a material, a coating material, which has a thermal expansion coefficient comparable to that of silica. Well, for that reason, we developed the liquid crystal monomers, and what you can see on the right figure is that indeed the material has a low thermal expansion around room temperature and has an even negative thermal expansion at higher temperatures along the orientation direction of the molecules. So if you can align these materials on your optical fiber, then you are basically dealing with a very small or even negative thermal expansion. And negative is not so bad, because that leads to tensile stresses on the fiber, which even keep them more straight as needed. So on the other hand, in the direction perpendicular to the fiber, of course, we have a high thermal expansion coefficient. The volume thermal expansion coefficient of these materials is comparable to normal polymer materials. The reason for this behavior is that when you are heating the sample, you go from a highly ordered state. This is exaggerated here in real time. It is not as ideal as shown here, but upon heating, you are decreasing the degree of order, which leads to a minor contraction parallel to the alignment, and expansion perpendicular to that. And only minor changes in the order parameter of the system are already sufficient to create this special behavior. So we could successfully coat an optical fiber at that time, but at that time we had a problem. We needed to have companies, chemical companies. I was working for an electronics company, Philips, who was not willing or capable to produce organic materials on a large scale. So we had many discussions with other companies at the time, trying to make them enthusiastic to produce the materials, but we did not really succeeded. Also because the commercial interest, it was commercially not so interested for most of the companies to target this market. So that basically could have led to a stop of this process. But then, because we had this process in hands, we could actually make use of other properties of the material, and the property that was most interesting at that time were the anisotropic properties. Just like normal low molecular weight liquid crystals, they are anisotropic in their properties. They have a low ordinary refractive index and a high extraordinary index. This is the index parallel to the measure to the director of the system, the orientation direction of the system. This is the index measured perpendicular to that. This is just the behavior of the monomer in the monomer stage, just behaving like normal liquid crystals, so high difference, high birefringence, and when you heat it above the clearing temperature, when materials become isotropic, you end up with one isotropic index. Well, as soon as you start polymerizing this sample, you keep the optical anisotropy, but then the temperature dependence become basically far less. Still a minor change because of the volume expansion coefficient, but much more stable than that of low molecular weight crystals. And for that reason, the material became actually of interest for the upcoming display market at that time. Liquid crystal displays were developing, they were improving and improving, but still had a number of problems to solve. The viewing angle was not always right, the brightness was not always correct, they were not so robust. And actually that's where the materials could function, and also for that reason, companies like, for instance, Merck also started to have programs on this in this area, and actually for a long time I worked together with the Merck people to develop the liquid crystal materials. Of course, the liquid crystal displays are at that moment replaced by other techniques, but still there are optical applications of interest, for instance, the near-eye optics that are presently developed for virtual VR applications of our applications. So this is a new area that is coming up. And meanwhile, we at Philips, but also at Merck at that time, we developed a whole range of liquid crystalline materials, all with this kind of more or less general chemical composition. So normally they consist of an aromatic core. They have a flexible spacer. You need some flexibility here to decouple the polymerization from the order of the mesogenic unit. Normally alkaline spacers, but you can also have ethers. And then we have the polymerizable end group. In most cases, we are using acrylates or metacrylates, but it can also be vinyl ethers, epoxides, or oxytanes, and we basically have synthesized them all. So in our research lab, most of the monomers were actually synthesized in my Philips time, but while making the transfer to the university, I could take actually many of the materials with me. So we have now a whole stock of more than 100 different liquid crystal monomers. So we can really play with the properties both in the monomeric state and in the polymeric state. Well, as said, the display interest is becoming somewhat smaller because other technologies, display technologies, is taking over. But then we started to work on tangible mechanical deformation. Well, if I say we, actually many people in the world making that step. But the mechanism is again based on the same mechanism for which we had the nice thermal expansion properties. Change of the molecular order leads to dimensional changes of your samples, and you see on the right just a few examples to which I partly will come back in my further lecture, and maybe I could activate this one. So this is moving more and more towards the soft robotic application. And typical triggers are temperature, light, electrical or magnetic field, and the changes in the environment, such as humidity. And as said, mechanism is comparable to that of the negative thermal expansion coefficient, change of order parameter, which means that if you, for instance, create a film, a thin film, where you have a splayed alignment, and with splayed alignment, I mean a parallel alignment at the top and a perpendicular alignment at the top. You can easily create this by playing with the interfacial conditions when you are making the films. Well, then you can already imagine that if you make a film like that, you will have, if you heat it, you will have contraction, according to this line at the top, and you will have expansion according to this line at the bottom. So the film has to start bending, just like a bimetal would bend. But of course, this is a monolithic material with a gradual change in the director over the thickness of the film. This is by heat, but you can also do it by light, for instance. And light trick morphing, well, the most common material that is used for that is an azobenzene molecule, which can go from a trans state to a banded cis state in a reversible way, just by exposing it in the absorption band of either the trans state or the cis state. And for that I should mention actually the work of Tomiki Ikeda and Yan-Li Yu at the time in around 2000, where they create liquid crystal films that they could address by polarized light, and then you could, making use of this polarization sensitivity, can actually change the direction of deformation by changing the polarization of the light. They also create already a kind of motor system. I'm always jealous about this device. They make a belt of this material, they expose it with UV light here. The film builds up some stresses because it wants to bend, and it can, so it starts to, and it can release the stresses just by rotating. And you can bring it back to the trans state isomazine by exposing it with visible light. Also in our group, we were working on that, and actually we found that we only need a very small amount of azo compound in the material to get already the bending properties. So this is the work of Casper. We make the inkjet printed the material in a splayed state, and then just by exposing it with UV light, the finger starts to bend. The movie is a little bit blurry because it is taken underwater to avoid photothermal effects, but the bending is obviously there. So from there, at this moment, actually many groups in the world starts to work on these systems. For instance, the group of Timothy White in Colorado, but there are many others to be mentioned. I just showed some work that we did ourselves. So, for instance, we created a continuous wave in a small film. If you make a film, again, we make a film with a splayed configuration. We bring it in a kind of banded structure. We fix the endpoints and we start exposing it with light at one point. At the point where the light hits the film, it wants to bend away. But if it bends away, it has to bend up at another position, which then will be exposed. This is just one example. You can play tricks with it. For instance, you can build it, bring it in a frame, and then you can create small walking grasshoppers from it. This is another example, much more recent. It's by a student in our group who wanted to mimic mimosa, and for that he integrated some electronics in the liquid crystal. So here we have the liquid crystal film. He made them sensitive for touch from his finger, and then the electronics do their best, mimicking the mimosa, where also the leaves gradually from one side to the other starts bending. But that's so these are all very nice applications, and we also still work on that. But yeah, the question is always, is there a future for soft robotics? Because in general, the forces that they can deliver are not so high. We have, of course, already very solid hard robots. So we were wondering whether we could make a kind of in-between step, and that is by using the same materials in surfaces. So we want to make use of this morphing behavior, not as a film or as a device, but as a part of a device. So you bring it as a coating, for instance, on a robotic hand, or but it can be also just on plain surfaces as a table. So this is the idea, that we can create structures in the surface which you can actually feel or can perform functions. And this is our somewhat older work in the first steps in that reason. So for that reason, we designed a blend which contains three basic elements. Of course, the liquid crystal monomer base, but we also added chiral component in the system, and we added the azobenzene, and this is the photoinitiator to polymerize it. So you make a so-called chiral nematic polymer film where the molecules are forming a helicoidal structure with the helix axis perpendicular to the surface. And now, after polymerization, we start actuating the azobenzene locally by light, and then you indeed, just as with the thermal actuation, you change the degree of order in the helix, and for that reason, at the position of the where you expose the film, it starts to expand. The expansion is rather high, actually. It is about 10% of the film thickness. So a 10 micrometer film gives 1 micrometer thick protrusions, which were a little bit higher than we could explain just based on the other parameters. So we dive somewhat further into the study. And what we also could find is that the decrease in order also created free volume, and that is shown in the experiment on the left. So here we have the film. We have the film with azobenzene and a film with tinufin. This is the reference sample, which absorbs as much light as azobenzene, but doesn't give the transist deformation. So then we start exposing it. The film is sinking. We have added some salt to the water to get the density right, and then you expose, and what you see is indeed that the density decreases and the film starts to float. The reference film remains at the bottom, and as soon as you switch off the light, it will sink again. And just by doing many experiments with different salt concentrations, you can estimate that the density changes from 1.2 to 1.1, about corresponding to the 10% of the deformation. But that is not the only thing that surprised us. Also the fact that, I mean, the materials that we made are glossy materials, or hard materials like Perspex. And it was a little bit difficult to imagine that these films could easily form the surface structure when you are actuating them. For that reason, we started to also look at the mechanical properties, and then we found that during the exposure of light, also so-called photo softening took place. So basically, by exposing with light during the continuous action of the azobenzene, the modulus changes. You go through the glass transition of the material, and it becomes flexible. It's shown also a little bit in the movie. If you expose, if the sample is outside the light spot, it is hard and glassy, and it's in the light spot, it becomes rubbery. So having developed this, we want to actually get rid of this mask-wise exposure of these films, and for that we decided to rotate the helix axis to go to a so-called fingerprint texture. The rotation of the helix axis, normally if you put a concentric material on a substrate, the axes are more or less perpendicular to the substrate, but by playing a little bit with the anchoring conditions at the substrate, and by optimizing the thickness over the pitch of the helix ratio, you can create a condition that helices are formed parallel to the substrate. If you look through the optical microscope, you see structures like this. This is also why they are called fingerprints. In the black areas, the molecules are perpendicular to the surface. In the bright areas, different. So this is more or less this position of the helix. In the bright areas, they undergo from to the more planar state. And you can now imagine, if you expose with UV light, that you predominantly, if you change the order parameter, the planar areas wants to expand, and the perpendicular areas wants to shrink, right? Just because of the same for the same reasons as they had the anisotropic thermal expansion again. Moreover, Where the azobenzenes are oriented planar, they absorb also somewhat more light than when they are oriented perpendicular. And the overall result is that we go from close to a flat state. You see a little bit of surface structure because of my so-called Marangoni effect, to a much more corrugated state. So all the planar areas come up and the homeotropic areas go down in this case. And this, of course, leads to many different properties, but one of the properties is the change in the change in friction coefficient, which could, for instance, be used to as a gripper. This figure again shows the change in height. This is in the flat state, a little bit kind of Marangoni. This is in the actuator state, where you have a high surface profile. Well, this is the switch from flat to corrugated, but actually we were even more interested in the switch from one corrugated state to another corrugated state. And for that reason, we had to work on a principle to develop a film that is already initially having the initial corrugation. Well, if you start making the film as such, I already mentioned the Marangoni effect, you will have a low surface tension in the perpendicularly oriented areas, and you have a high surface tension in the parallel oriented areas. And that leads already to this initial surface structure. However, if you start polymerizing, the polymerization shrinkage is higher parallel than perpendicular to the orientation. So basically you are counterbalancing the initial surface alignment, and you could even get a negative alignment. And this is not what you want. So we have to find a trick to come to a more initially a higher oriented state. And for that, we developed the process of director-steered polymerization-induced diffusion. So you can imagine that if you have your helix like this, and you are now developing a special photoinitiator, which is dichroic in nature, you might understand that you will have a high absorption in the planar area, where the photoinitiator is also planar. Photoinitiator aligns with the liquid crystal, and you will have a low absorption in the direction perpendicular. Yeah? That means that the polymerization rate in this area is higher, and during this polymerization, a diffusion process is initiated where molecules diffuse from the slow polymerizing areas to the fast polymerizing areas. And that creates a system that at the end, you create a polymer where you have a large modulation of the height with the parallel molecules in the hills and the perpendicular molecules in the valleys of this system. This is one way of doing it. This is work of by Feng in our group. Another way is not using this dichroic photoinitiator, but now just going to a system where you have added some dichroic dye. In that case, you create just the opposite. The absorption of the light intensity is then higher in the perpendicular area, where the dye does not absorb the light so much, and the light intensity is lower in the perpendicular area. Then the opposite happens, what is happening here. So during the polymerization, the molecules tend to diffuse to the homotropic area, and now you have a system where you have hills where the molecules are perpendicular, and you have valleys where they are oriented planar. And now you can start playing with this. You can basically start inverting this system. So if this is the case, homotropic areas are higher, then you start actuating. This will shrink, this will actuate, and you go from one state that the hills become valleys, and the valleys become hills. So you're basically inverting the surfaces for this. And this can, for instance, be used to play with the adhesion properties of the surfaces. So I help you a little bit through the composition. So again, we take the normal composition of liquid crystal monomers. We have added the chiral component to make it chiral, such that we get the thickness over pitch ratio correct. We have added the dichroic dye to slow down the polymerization in the planar areas, and we have added an azobenzene to make it actuation. So now we are going to from a state where we have, if we have polymerized it, where we have the homeotropic areas in the hills and the planar areas in the valleys. And of course you can invert that by UV light. Now if you now apply an adhesive, pressure sensitive adhesive at the top of the films and releasing layer at the in the valleys, you can actually switch it from a system where the surface is mainly adhesive because of the pressure sensitive adhesive to a surface which is mainly releasing because we are just hiding the pressure sensitive adhesive in the valleys. And one of the things that you can play with it, and here you see the difference in adhesion strengths. This is measured in hair. This is when the adhesive is at the top, high adhesive force. This is when the adhesive is in the valleys and low. And it works because we work this protein-like adhesive, basically inspired by the muscle proteins that they use to adhere to the stones in the sea. Well, it also works very nicely underwater. This basically was the hobby of Wij. He wants to have a system was adhering in water, but it works also in air. And here you see the inversion again. So again, this is about real time playback. We only accelerated 3 times, and you can see that we can very rapidly switch from one state to the other. Valleys become hills, hills become valleys. And now one of the tricks you can do with it is make a kind of pick and place system. So now we have the adhesive side to the copper plate. We expose with light, then the adhesive side goes inside, and you can release the system. So far I have discussed temperature and light mainly to actuate the surfaces, but you can also use electrical fields. And this is an example where we have the material applied on an interdicitated electrode. This is just the real sample. This is the activated area. We created a system where we have homeotropic orientation, so molecules are oriented perpendicular to the surface, and now we start actuating, and of course we hope that we will have expansion in between the surfaces, and the expansion should then as a result of the volume that we are creating in this this case. And this is the interference measurement in the off state. Well, you see the pattern of the electrodes. In off states, the patterns of the electrodes are higher, and as soon as you start actuating, it starts the structure start to form. And this is the movie related to that. Again, this is the position of the electrodes, and upon actuation, we are forming this volume, this free volume, and the surface starts to expand. The frequency that you need for this were relatively high, so the system starts to work only around above 400 kilohertz. I come in a minute to the explanation why. So you need to drive the system at high frequency, almost at radio frequency, and of course it scales also with the field strength that you apply. Typically we are applying 40 to 60 volts between the two electrodes. We did some study, laser spectral imaging studies to that, and we could basically, upon the actuation, see 3 regimes. First, if you start with laser spectral, you can get information on the mobility of your cells, of individual molecules. So basically, if you start, you see some messages randomly move a little bit Brownian-like. Like a Brownian motion, but the amplitude is relatively small. Then as soon as you start applying the AC field, you come in a regime where the amplitude of the molecules become already larger, and slowly the molecule starts to create a free volume. And then at a certain moment, the network becomes plasticized. So suddenly the motions become large in this case, and basically you can see that it is occurring at this 400 kilohertz that I just mentioned. So this is the moment that we have plasticization, and the material goes through the glass transition, and the expansion can take place, and the free volume can then next being formed. The deformation is, however, rather unstable, so you can see here. So it's not a simple expansion, and if you switch off the light, it goes away. So we had to find some explanation for that, and the explanation that we came up with, it is not a proven explanation yet, it's just a postulation, is that the electrical field resonates with the network to resonates with the eigenmodes of the networks. Then you have resonance. That is the moment that you start creating the free volume. But as soon as you have the volume created, the resonance conditions are changing, and the system falls back to its initial state. But then it starts becoming actuated again. So this is a process that is continuously repeating itself. So this was electrical actuation of homeotropic films, but the question came whether we can also use this for the cholesteric films, the chiral films, the fingerprints, so to say. So we basically used the same system as we had before. Very important is the presence of this very polar group, which interacts heavily with the electrical field, and then by doing the actuation, we just see the same as we saw with light. Again, the valleys becomes hills, and the hills becomes valleys, and this is also more or less real-time actuation of the surfaces. And one of the applications that we developed, this was my thing again, was to use these type of surface modulations to clean up glass, or to clean up a substrate, for instance, to be considered for the solar cell cleaning. So this is the sample that we have here. We brought some sand on it, model sand in this case, and we start actuating. So this is the sand. On the monitor you can see the moment of actuation, and as soon as it's actuated, the sand is removed. Basically, we have the two effects here. We have the high frequency modulation we saw just before, and we have the surface inversion. So we have a two-step mechanism for the removal of the sand. I will make now one step to a somewhat more complicated system. So I just discussed the fingerprint textures of the liquid crystals. Well, already in a very early phase, when we started creating fingerprint textures, we saw all these little dots in between the real fingerprints that we want to have. And our first targets at that moment was to create conditions to reduce this number of little dots. But later we became more interested in the dots by themselves, and they appeared to be toronic structures where the molecular orientation rotates from perpendicular in the black area to this 180 degrees rotation to the center, and that in all directions. So, and well, for that we started already also a collaboration with the group of Ivan Smaljuk in Colorado, who is of course one of the world experts in these toronic type of structures. And while doing it, Jacques and Darian, Jacques is our student, Darian is Ivan's student, they were developing, they were optimizing the conditions to cover the whole surface with these torrents. And you can imagine that if we now start actuating these torrents, you will have the kind of same principles as with the fingerprints itself. So in the areas where the molecules are perpendicular, they tend to shrink when you reduce the other parameter. When they are planar, they tend to expand. And that is also what you basically see. In this case, the film covered with torrents is heated. And if you look very carefully, you see a little bit of volcano type of structure. That is where the shrinkage takes place in the thoron, and the surroundings is the planar where it starts to expand, and then at the edges it starts to shrink again. And you can also play with the inversion again. If you polymerize it at a somewhat higher temperature, then that temperature gives the flat state. If you cool down, you will have just the inverse of the heating. Then the planar area starts to shrink, and the perpendicular area starts to expand. And sorry for this. And then by heating, if you go through this temperature of polymerization, then the opposite will occur. And working with these thorons, using the expertise of Ivan, basically what we can also do in the monomeric state when we have the thorons, we can just pick them up by a laser tweezer, and you can place them at positions where you actually want to have them. In this case, we created our TUE logo in this case. And again, you can actuate them. The planar areas goes up in the heating state, but goes down in the cooling state. And this is the cross section of the thoron. So again, a volcano type of structure. And by placing at the right position, well, you can make our university logo more visible. Make a small step now to other surface structures. For this reason, we are using not our pure monomer system, but we go to the so-called liquid crystal elastomer surfaces developed by a number of groups in the past. Where you have a reaction between the liquid crystal monomer and a tile to form an oligomer, and the orientation is then take place in the oligomeric state, and then the photo cross-linking takes place to freeze that orientation in. And the advantage of this system is that you increase even more on the robustness of the systems, but also on the mobility. You are basically bringing the class transition to lower values. Well, if you do this now on a surface that is having a surface alignment technique, it has been treated by surface alignment technique, so you have basically an azimuthal type of surface alignment. Yeah, this is the orientation of the molecules. And if you make this film and you look through the optical microscope, you should see a structure like this with the various defects in the control defects in the systems. Well, you can already model, and this is done by Yusuf in our group. You can already model that, by the way, using this mating structures, you can already model that you have expansion in these areas and this defect. You will have also expansion in these defect positions, and you will have shrinkage in these areas. So if you make a film which is initially flat, if you start actuating them, and that can be done by temperature or by light, you can go from an initial flat state to a corrugated state like this. And special here is that the corrugation is now even much higher than we could get with the pure liquid crystal networks by themselves. I make another step because I want to finish with coming more and more to the soft robotics experience that we propose. You can also go to a surface where you have more or less fibrous structures. Also there you can use the liquid crystal elastomers. They have a viscosity such that you can easily draw fibers from the surface, and then just by actuating the fiber, you can actually modulate the orientation of the fiber. In this case, we do it by heat. We have a small electrical heater in the foot of the fiber here, and then by heating it, you have the director is going from planar here to perpendicular here, so it gives the local change of position. But you can of course do it in other position, and then it moves to the other direction, and that is what Sam Weimar did in our group. So he created a small array of these fibers, and just by playing with the local electrical heating, and you coupled in this case to this mobile phone, you could basically create the bending direction. Well, this all brings me to a field that we have now are now working on. This is one of our main topics in the group, haptics, and we try to create surfaces that could interact with, for instance, human. We have shown that we can switch them between flat and structures. We can switch them between structures and inverted structures, between hard and soft, between sticky and non-sticky, and between flat and erected microfibers. Also, we can switch between dry and wet, but I will not cover this topic here. But here you see some examples that we can do at a surface. So this is the aim that we have. So you have to create communicating polymer surfaces. So we want to make the surface that we make part of an object. The object can be a computer by itself. So then you are making kind of hybrid systems, soft computing with hard computing. But it can, for instance, also be a steering wheel that you give you information while you're driving. But it can also be a screen of your computer at home or of your laptop, where you can also sensitive haptic information from. And as said, you can switch between flat and corrugated, and this information is given to the person in contact or another computer in contact with this surface, and that can be developed to a system where you can really exchange information just by surface contacts. Yeah. So here you see some examples that we are working on. So touchscreens we are working on. We are working on making screens more accessible for writing conditions, so you can have local surface roughness to enable easy drawing and writing, but the transparency in the remaining part of the screen is still there, because the rest of the surface beyond somewhat further away from the tip remains transparent. And we are collaborating with blind institutes to develop Braille type of applications for this. And one of the aims that we have there is to make actually Braille type of systems which are more complicated, for instance, to give geographic information on maps. This is a mock-up. We have not realized this yet, but this is the real structures that we can create for these type of applications. We also created a startup company. This is Matt. He is now leading that company in our group, and we hope to develop these applications somewhat further. Well, this brings me to the end. I went back in the past by the application of communication fibers, and also with the applications within the flat panel displays. And I showed you some of the present and the future where we have developing sensors and actuators, and also some potential for robotics, communicating surface, and haptics. And with it, I would like to stop, and I'm open for